Hello everyone, this is Jake from Natural by Nature, and today I will be discussing my math paper that I published in 2021. So, obviously this is my main channel, Natural by Nature. Some of you may have seen me from my other channel, Jake TGM. That channel is now gone, and so I'm on this channel. So this is my main channel. This is also where I will be posting the Tub Talks, which is the podcast with my dad. However, I will also be posting videos with me, just either going over like math or any other thing just related to my life. And I'll be discussing that all on this channel here. So yeah, as I stated already, to reiterate, I will be going over my paper, my math paper that I published to GSJ back in 2021. What you're seeing right now on the screen is a reformatted version of the paper. So essentially I wrote up the paper in LaTeX and just added some extra tweaks and extra things to make it look better for you guys. But it will be the same similar concepts. We'll just be going over each question in the paper, how I solved them, my thought process, and yeah, let's get to it. Okay, so starting with question 1, we have, I'll just read it out. If we look at the following equation, assuming psi is psi t, we have that. So, namely, we have psi to the psi, the derivative of that, plus the integral of I to the I, divided by the definite integral with the upper bound of negative sigma 2I, and the lower bound tan t psi, and then we have that times the triple integral of t. So we can solve for an approximate solution. First, we're going to focus on the derivative of psi t to the psi t. Obviously, there are different ways you can approach this question. This is just the way I approached it when I initially calculated it, so that's the way I will be doing it for this video. So, let's write this out. We have psi t to the psi t, and we are deriving that. So, first thing that you might notice is this looks very similar to something you would probably see in Calc 1, namely d by dx of x to the x. And sure enough, it's exactly the same concept. So breaking this apart, we have psi t to the psi t. Deriving that, we get ln psi t, so the natural log of psi t, multiplied by the derivative psi prime of t plus psi prime of t. Sorry, I forgot to put brackets here. This is all going to be multiplied by psi t to the psi t. So that's the fully expanded form. And now that we've solved this, it is fairly simple. We're just going to plug it back into the original equation. It's quite redundant, and you could probably see, how to do it. So I won't be plugging it into the original equation, as I've already done that in the paper and you probably saw it. But we will move on to the next step. So the next step revolves around basically simplifying the indefinite integrals. The indefinite integrals are easier than the definite integral in my opinion, so that's why I started with them. However, again, it's completely up to the person solving it. If you want to solve the definite integral first, that would also work. But I will be solving the indefinite integrals. So let's write out the equation. We have our solution up there. I'm just going to write it as dot, 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 but this just represents the solution we had up here. So dot, 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 which is just that, plus the definite integral of I to the I, which is of course just I to the I t plus c, because it's with respect to t. Then we take this over, because it's a fraction, and we have the integral with, I'm writing dot dot dots for the upper and lower bound, because they're quite long and complicated, so, but you know what they are. It's just negative sigma to the 2i tan t psi t. So then the triple integral of t is simply t to the 4th over 24 plus the constant c times t squared over 2 plus the constant ct plus the constant c dt. So it's just that, just breaking that apart. Now, another thing that you might be able to notice almost immediately is that with the definite integral, now we can apply the sum rule now that we've taken out the triple integral. And so we're going to deconstruct the definite integral via the sum rule. So we have, again, lower upper bounds of t4 over 24 dt. Then we have definite integral c t squared over t dt, and you get the point. Just exactly all of that, analyzing that. And once you calculate those derivatives, you plug it into the bottom part of the equation, and then you have a fully simplified equation. And that's exactly what the question wants. So yeah, that is question 1. All right, now moving on to question 2, we read the following. We will now approach the following problem, namely alpha minus beta to the 4 minus tangent x, delta times negative x plus cotangent x over the fraction of negative I root 3I over I plus x to the I infinity times infinity to the negative I times infinity times I, all of that subsequently multiplied by I to the negative I plus I times x, multiplied by the root of infinity to the negative I, multiplied by xi multiplied by 30 degrees. Okay, so starting this, we will break up the equation into 2 separate fractions, because obviously we see the first one as a fraction, we want the other one to be, so we can eventually combine them. So we have negative alpha minus beta to the 4 negative delta tangent x. Also note that this delta is not the Kronecker delta, it's just delta representing a variable, but yeah, same sort of concept. Okay, so cotangent x over root 3 root I, and then we add this. So the 30 degrees, after simplifying, will become 180 degrees times ix times I plus I to the infinity plus 1. So again, this is just simplifications. It's not too difficult, so I'm not going to go over exactly how to do these simplifications, but they are quite tedious. So times I squared. And all of that will be over 6. So now this is perfect, because we have it separated into 2 fractions, and we can simplify both subsequent fractions and then add them together when we feel like it. So if you look at it, you can notice a couple things that we can do, okay? So if you note the root 3 root I on the bottom, we can actually simplify that by taking root 3 root I, bringing it to the numerator, and having the denominator as 3I. So that's one way we can simplify that equation, or that particular part of the equation. And then we could subsequently simplify this more by taking off the root 3 root I and instead having the denominator as root 3 root I. So eventually we will, of course, bring the root 3 root I down to the denominator again. We're just doing this to simplify the equation on the top a bit easier. You don't actually have to do this, it's not necessary, but eventually we're going to multiply root 3 root I on the other fraction, so in that case it would be relatively easy and relatively convenient. So bringing this down after doing all the simplifications, and of course finding common denominators between the 2 fractions, we have negative alpha minus beta to the delta tan x minus delta tan x, okay, cotangent x, I don't have a lot of space, but yeah, plus 4 goes here, all over root 3 root I. And then we're adding this to root 3, 180 degrees, I to the 3 halves, x to the I plus I to the infinity, plus 1. So that's all in a fraction, or all in an exponent there. Then you have, sorry about that. Let's fix that, just wait. Okay, I up there, and you have infinity, negative I over 2, and then you have that multiplied by infinity to the negative infinity minus I squared. And then all of that is going to be over 6 times root 3 root I. So you can actually connect the two if you wanted to. However, this is as simplified as I wanted to go in the equation itself. But yeah, that's how you break down question 2. So let's move on to question 3. Now, if you noticed during the second question, I went relatively fast through the steps and everything. That's just because, certain things that I think the audience will understand and, it would be intuitive to them. I don't need to explain that. So usually I don't end up explaining that stuff. And with the easier questions, I won't do much explaining. However, once we get to the more complex ones, I will analyze them, on a more full basis. So anyways, looking at question 3, we view the following equation in its entirety. So basically all it is, it's a bunch of divisions. So it's like, if you think of it, it's like a tower of divisions, which is relatively simple. Of course, I threw in some difficult terms there that you have to deal with, but other than that, it's not bad. So anyways, if you divide the easier values, so namely x, x3, x5, x7i, all of those, they're relatively easy to divide. You can break it down into a simpler fraction. Namely, you have x over root I times x to the 9 tangent of x plus 61 minus I, and then and then that's multiplied by x to the 7i plus pi. This is all over x. And this is subsequently over x to the 13i. So as you can see, it's obviously a lot easier, this expression. Next, we can apply the fraction rule. Okay, so if you remember the fraction rule, we can apply that in this given scenario. So I'll just move it down here, which would eventually give us x over, and then we have in brackets here, x to the 7i plus pi. We have root I times x to the 9 tangent of x plus 61 minus I, x to the 13i. So again, much easier now, and especially when it comes to simplifying it, we put it in, relatively simple expression that we can now deconstruct. So dividing this out and doing a bit of simplification, we have x to the negative 9 tangent x plus I minus 60, and then we have all of that over x to the 7i plus pi, so that remains the same, and then we have root I x to the 13i. Okay, so we have this all in one easy fraction now. Again, manipulation of the denominator will help us more and will help with, I guess, the concisity of the equation. So remember, we're just trying to go for the most concise we possibly can. So multiplying this all out and doing a couple more substitutions and simplifications, we have negative 9 tangent x minus 12i minus 60, all of that over I times x to the 7i plus pi. So this is the most concise form that you can get it in. And yeah, that concludes question 3. So let's move on to question 4. All right, so moving on to question 4, we note the following problem. So you can see it on the screen here. The one with beta squared times x to the I to the root 3 and so on, so on. So we could start by rearranging and simplifying. So one thing you could probably already notice is that the top and the bottom equation are the same. However, before we do any manipulation where we just cross one out, we are going to simplify. But we will eventually do that, you'll see that. And this is actually a relatively simple problem. It's like 3 steps or whatever. Just a little brain teaser just to catch you up to pace with what we're doing here. So we have phi to the x minus 3x over psi, sorry about that, x looks really bad, minus root, the cube root of 2i. So we note that we can deconstruct this and we can provide its logical equivalence. So in this case, the logical equivalence to that would of course be 5x to the negative 3x minus root 2, so we're deconstructing the roots, so we're taking root 2, root I, and that would be all multiplied by psi, okay? And then this would be all over psi. So this is just a cleaner way of representing it. And then the rest is quite easy. You're just noticing that, like, if you have, in this case, let's say you had like x and over x squared, it's the same as taking out this x, taking out that, which leaves you with 1 over x. It's the same sort of idea. It's just to kind of like trip you up. Once you see it, you're like, oh, this looks incredibly difficult, but actually no, it's quite simple and it's in its roots. So yeah, I'm not going to show how to do it. It's just taking 1 over and then the equation below. And yeah, that's question 4, so we'll now move on to question 5. Alright, so moving on to question 5, we see that we note the following expression. This is the one with the massive square root over the 2 subsequent fractions. So we could start by solving the integrals. So if you see at the bottom, we have the cube root of the integral of tangent x dx. And then on the second fraction, we have on the third, I guess, row, yeah, whatever you want to call it, or third denominator, we have the integral of tangent x. So this is fairly simple. If you've done basic calculus, this will be fine. So you just you have the massive root over here, you have negative I root I right here. This is supposed to be exponent, by the way, but then you have the cube root, and in this case, taking the integral of tangent x. So the integral tangent x dx is equal to negative ln absolute value cosine x plus c. Okay, so that will go there. So we're plugging that back into there. And those are both the same, so for the second fraction, it's also negative ln absolute value cosine x plus c. Okay, now we will simplify the ith root. Okay, so in the first expression, we have negative I root I, and we could simplify that because negative I root I, sorry about that, negative I root I is exactly like saying I to the negative 1 over I. Okay, same exact expression, same exact expression. And then that's going to be plugged into the initial equation, just like we plugged in the integral of tan x. So now, when we remove the cube root and we apply the numerator, we can get a more simplified equation. So namely, we have massive root here, we have I to the negative 1 over I, which we already previously defined. Then we have negative ln, absolute value cos x, plus c to the 2/3. We have that on the top, and then we have negative ln absolute value cos x plus c, no braces there, no bracket there. And then this is of course added by, and this is also under the square root, sorry I don't have enough space, but yeah, that's also under this part's also under the square root. So we have add the other fraction, subsequent fraction, in which we have the cube root of I, cube root of I, and that is multiplied by tangent x, cotangent x. And that is all over negative 3i plus 2, which is over negative ln absolute value cosine x plus c. So yeah, easier expression now, easier to deconstruct and deal with. So what we can do is actually take the negative 3i plus 2 and apply it to the numerator. I'm not going to go over that step, it's fairly simple. And eventually we are going to have to add the expressions together, but it's fine because we have both the denominators to be relatively the same thing. So it's easy to solve in that case. It'll be a long drawn out expression, but the formulations underneath it are relatively simple. So yeah, that's all I'm going to go over, and that is the conclusion of equation 5. And yeah, let's move on to question 4. Alright, so question 6 states that you are given a third-degree polynomial function with the terms listed below. You are tasked with simplifying the expression to a binomial. You then must take the derivative of each of the components in the original polynomial. Once this is completed, you must plug each derivative into the initial equation. After this is done, simply solve for x. Lastly, take the product of all x values. So it may sound complicated at first, but essentially we have a polynomial of the form ax3 plus x squared b plus a squared x over dc plus 2ab over dc plus b squared over x dc. And this is all equal to 0. So we must find something that can multiply to give ax plus b on both sides. Namely, we can take ax squared times ax plus b, right, on this side. So if you factor out the x squared, you find that ax plus b is left on the inside, which is exactly what we're looking for, and it's similar in this case. So we have cd dc times, in this case, instead of ax, it would be cx plus d is equal to 0. Okay, so this is an issue because obviously we don't want cx plus d, we want ax plus b. So what we can do is we combine the outer parts together, so the outer parts here, and we can find a different formulation in which we can arrive at ax plus b. So we have x squared ax plus b plus, and then now we're going to have ax, sorry about that, ax plus b on the top, on the numerator, and we have dcx on the bottom. And this is all multiplied by ax plus b. So obviously if you break this out, you can find that it's exactly the same as the initial expression. Just simplified and put into the form that we want it to be. So now, after this, we can create our binomial expression. So we'll have here x squared plus ax plus b over dcx, all of that, which would be times by ax plus b, which would give us 0. Okay? Now we will take the derivatives of each parts within the initial equation. And in this case, we're going to assume that a, b, c, d are constants. All right? So these are constants in this case. So we have that f of x is equal to ax cubed. So this is the first component. So taking f prime of x, or the derivative of x, we arrive at 3ax squared. All right? So remember, we're just manipulating the x in this case because a is a constant. So it's just, for example, if you had like 4 times that, that would be a in this case. So then we have the second component, which is f of x is equal to x squared b. All right? So f prime of x is equal to 2bx. Okay, so fairly simple derivatives. It's fairly simple derivatives here. And then we have f of x is equal to a squared x over dc. That's our one right there. And so finding f prime of x is relatively simple because f prime of x is just going to equal a squared over dc. Right? Because remember, x is just going to be 1 because the derivative of x is just 1. All right. Then we have f of x is equal to 2ab over dc, and this should be very intuitive because derivative of constant is 0. So that will just equal 0. Okay, bringing it down, we have f of x. This is the final one, the fifth expression. We have b squared over x dc. So f prime of x is going to equal negative b squared over x squared dc. Okay, so we can now move on to the second portion of the question itself, which states that we have to set each derivative equal to the initial equation and solve for x. So we'll start with our first expression, which we defined up there as f of x equals ax3. So we're plugging in the derivative, so we have 3ax squared is equal to ax cubed plus x squared b plus a squared x over dc plus 2ab over dc plus b squared over x dc. So now we can simply solve for x. So we'll divide, I would start by dividing everything by 3a, and that's exactly what I'm going to showcase here. So anyways, dividing all of that by 3a will give you x squared is equal to ax cubed over 3a plus x squared b over 3a plus a squared x over dc over 3a plus 2ab dc over 3a plus b squared over x dc over 3a. So yeah, fairly simple, just normal algebra. Then, of course, we have to isolate for x, not x squared, so we'll take the root. So we have x is equal to the root of everything that we stated up there. So all the exact same expressions. And we can put them all into one fraction. I'm not going to go over that, but that's exactly what you would do in this case. So moving on to the second polynomial that we described up there, which in this case is 2bx. So 2bx, we set that equal to ax cubed, so forth, the exact same equation. It's just the initial equation. So again, here we would divide everything by 2b. X is equal to ax cubed over 2b, etc., etc. And it's the same exact thing, except this time we don't even have to take the square root. It's just in the form of x, so we have already solved for it. And we can, of course, put it back into one fraction, which is what we will end up doing. Okay, third one, we have a squared over dc. Set that equal to ax cubed, etc., etc. Now this one's a bit more tricky. However, it's still fairly easy. We're going to multiply everything by dc. So we have a squared is equal to ax cubed times dc. Same thing, you're going to times everything by dc there. And then we're going to put it into one fraction, right? So we have a squared is equal to x times, and x will be multiplied in this case by ax squared dc, etc. We're just basically factoring out the x in this case on the top portion. And we're dividing that by x. Okay, so these would cancel each other out, but that's what we want. Because now we can do this little neat trick where we take a squared and we swap it with x. So this will then solve for x. So we have x is equal to x times ... over a squared, where, yeah, ... is just the factored out version. Okay, now we have fourth expression, namely we have 0. So 0 is equal to ax cubed, etc. This one's fairly simple. We're just going to combine the DCs, so the two fractions that are over DC, and we'll combine those two together. And then after that, we can divide everything by ax plus b, which gives us x squared is equal to x times a squared x plus 2ab. And I'll actually write this one out in its entirety. B squared over negative a dc x squared minus x dcb. Okay? And then we're just going to take the root. However, when we take the root of this, we'll note that there's an imaginary part. So we will take out that imaginary part. So we have I times the root of ax plus b over x dc. So as you can see, it looks very nice, and it's in a nice clean order so that when we plug it in, or when we eventually take the product of everything, it'll be relatively simple. Lastly, fifth component, we have negative b squared over x squared dc is equal to ax cubed ... We're going to divide everything by x squared and multiply by dc, which will just give us negative b squared is equal to ax fifth dc, etc. Scrolling down. So then we'll set the equation to 0, and this will be done just by adding b squared to the other side. And then after that, we can solve for x quite simply. So we have x5 dc ... all over b squared. Very nice. Lastly, we are tasked with finding the product of all x values. So I'm going to do this by representing it in the form of capital pi, or product notation, in which we will let the 5 solutions above be represented as x1, x2, x3, x4, and x5, respectively. So, knowing this, we can use the product notation. So capital pi, where I is equal to 1, 5 on the top, and xi, which means exactly what I expressed here, where it's just x1 times x2 times x3 times x4 times x5. So all of them together. And then the rest is quite tedious because you actually have to multiply them all together to get a nice little fraction at the end. But I'm not going to go over that. It's fairly simple. It's just products, just multiplying all the equations that you already have. So yeah, that is the end of question 6. We will now move on to question 7. All right, so now we have question 7. So in question 7, it's kind of set up in a similar way. We are given a specified polynomial that can be seen below. We must solve for delta first, then use common properties of delta to solve for x. Note that h bar in this case is not Planck's constant. So writing it out, we have delta x squared h bar plus delta h bar y, and then plus delta squared x cubed plus delta squared xy minus delta y plus capital psi is equal to 0. So we have that polynomial expression there. So we're going to find the common multiples of the equation first, which is fairly simple, especially with this first given part. We have delta h bar times x squared plus y. This is just regular factoring. Add delta squared x taken out of x squared plus y, and this leaves us negative delta y plus capital psi on this side, and it's still equal to 0. So we can combine these outer parts. So I'll move this down here. Namely, we have delta h bar plus delta squared x multiplied by x squared plus y. And same thing, we have minus delta y plus capital psi is equal to 0. Then we can add the part that's not multiplied to the other side. So in this case, that would be the negative delta y plus psi. We could add that to the other side, and we can divide by x squared over y, which simplifies to delta h bar plus delta squared x is equal to delta y minus capital psi over x squared plus y. So that's fairly simple. Now we've deconstructed that. Again, this is relatively easy. We'll take the delta out and divide to simplify, giving us that delta as a whole is equal to delta y minus psi, capital psi, over h bar x cubed, add delta x cubed, add y h bar, add delta xy. Okay, so that's all a part of that expression. So we note that delta x essentially means x2 minus x1. This is using the common properties that I discussed before. So we can apply this logic to the answer, and we find for delta. So note in this case, there isn't a particular difference between x1 and x2. And this works perfectly for us because we can have the fraction that we defined up here, and we can multiply that by x, which is equal to x, 1 minus 1, right? Because it doesn't matter. x2 and x1 in this case are the same exact thing, so it's just the same as saying x minus x, which is 0. So plugging that in, you know that that times x is 0, dividing by x gives us that x as a whole is equal to 0. So yeah, understanding all the aspects of the equation makes the resubstitution and simplification a lot easier. Okay, so thank you all for watching. This is the first part, so I only went up to question 7 in this video. However, next video I will continue on and complete the rest of the equation. Below I will give the PDF to the paper itself, and I will also give, a brief description of everything and what the paper is and what it entails, and you can go check it out if you'd like. But yeah, thanks for watching, like and subscribe, and I'll see you next time.